Imagine for a moment that you are standing on the Baltic Sea coast, looking into the darkening twilight. You are completely alone. The nearest human is far, far away. Suddenly your attention is caught by a bright light above the dark horizon. At first looking like a spark, this quickly brightens up and splits into several individual light streaks. Within a few seconds, this light ball has become a searing flash. The blazing objects pass silently over your head, followed a moment later by a deafening blast. The ground heaves and a blast wave thrusts you backwards. A fiery, glimmery, mushroom-like cloud of dust and debris rises into the sky. When blown by the breeze, it leaves behind a dust-covered landscape. This may have been the terrifying sight experienced by early settlers of the Saaremaa island when an asteroid fell in Kali a few thousand years ago. The Kali impactor was apparently only a few meters across. But what might happen if a giant asteroid, hundreds of meters or even kilometers in diameter, targets the Earth? Then the explosive power of the impact would lead to devastating consequences, even to the extinction of all civilization. But what are the odds of being hit by a giant asteroid? Scientists estimate that every year the Earth gets bombarded by at least 20 to 30,000 tons of meteoritic material, which people usually see as shooting stars. If you have wondered what makes these cosmic fireworks, then you probably know that meteor showers are just the debris of passing comets, which get heated up when the Earth passes through their dusty tails, or sometimes the debris from fragmented asteroids. Every year in mid-November, if you can get away from the city lights, you can have a great view of Leonid's meteor shower, radiating from the constellation Leo. It is estimated that the annual Leonid shower may deposit about 12 tons of fine particles across the entire planet Earth. Besides the dust to gravel-sized cosmic particles that burn up when colliding with the Earth's atmosphere, bigger chunks of cosmic rocks enter our atmosphere each year. These small asteroids, which may range from basketball size to a few meters in diameter, can be observed as blazing fireballs traveling over the sky. They mostly burn up before touching the ground, but occasionally some of them may survive the voyage through the dense atmosphere. Such a rock that has landed on the surface of Earth is now called a meteorite. It is estimated that about 500 meteorites ranging in size from marbles to basketballs or even larger reach the Earth's surface each year. But only 5 to 6 of them are recovered. There are quite many records of meteorites successfully touching ground in several localities in Estonia in the 19th century. Kaande meteorites in Saaremaa, 1855. Igaste in southern Estonia, 1855. Pilistvere in central Estonia, 1863. And Tänasilma in central Estonia, 1872. All these were stone meteorites, weighing from a few grams to several kilograms. But NASA scientists have had the chance to study iron meteorites also on Mars. While traveling on Mars' surface in July 2009, the NASA rover Opportunity discovered some iron meteorite lumps lying on the ground. These meteorites displayed highly cavernous surfaces. But the primary mission of the Opportunity rover was to study Mars' meteorite craters. Therefore, the Opportunity landed in the 22 meters wide and 3 meters deep Eagle crater and examined the nearby stadium-size Endurance crater. Then it took a couple of years for the Opportunity rover to drive down to the Victoria crater. This view shows how the roughly 730 meters wide Victoria crater looks from a spacecraft flying 300 kilometers from the surface. The following flyby animation displays the crater image from a rover's point of view if looked over the crater's edge. matched by the actual panoramic view taken by the Opportunity rover. A further challenge for the Opportunity is to drive 10 kilometers southeast to reach the huge, 22 kilometers wide Endeavour crater. The scars caused by heavy asteroid bombardment can be well observed also on the surface of the Moon and on other planets lacking an atmosphere. These meteorite craters are exceptionally well preserved compared to those on Earth. By now, at least 170 impact craters have been identified on Earth. These craters range in diameter from a few tens of meters up to about 300 kilometers. 3 out of 5 of the world's largest meteorite craters are located in Northern and Central America. The Sudbury and Manicouagan craters in Canada and the Chicxulub crater in Mexico. This shuttle view shows the impressive 100 kilometers wide Manicouagan impact structure in Canada, also known as the Eye of Quebec, which was created by an about 5 kilometers wide asteroid. An even larger impact crater, the huge 170 kilometers wide Chicxulub multi-ringed structure, is buried by several hundred meters of sediments on the coast of the Yucatan Peninsula. The following illustrations are made by NASA scientist Bill Hartmann, depicting the Chicxulub impact which happened roughly 65 million years ago, when an asteroid about 10 to 20 kilometers in size crashed on Earth. Such large craters can be observed only from a spaceship, but if you want to get acquainted with the nature of well-preserved recent craters, then the Barringer, also known as the Meteor crater, in Arizona might be your destination. This crater formed roughly 50,000 years ago when about 30 meters wide iron-rich asteroid plunged into the Arizona desert, resulting in a 200 meters deep and 1.1 kilometer wide crater. The Barringer crater is a simple crater since it has no central peak or rim terraces. Now that you are armed with basic information about the meteorite craters on Earth and on other celestial bodies, let's take a close look at the most prominent meteorite impact sites in the Baltic Sea area. As you can see on the map, numerous impact structures have been identified here, but we will be introducing you to only the most outstanding ones from a geotourist and scientific viewpoint, namely the Kali, Kärtla, and Neogrund craters in Estonia, the Lumparn crater on the Öland Islands, the Söderfjärden crater in Finland, and finally, the Tvären crater in Sweden. The Kali main meteorite crater in Saaremaa is without any doubt the best known of all Balto-Scandian meteorite craters, because this is one of the few craters in the world where a meteoritic origin has been proved with full certainty by finding meteoritic iron. Actually, the Kali meteorite impact site hosts one large main crater and 8 small satellite craters in the fields of Kali village in central Saaremaa. Geological and geochemical studies have shown that this iron meteorite probably weighed at least 1,000 tons. While penetrating the atmosphere, it was heated up and was broken into several pieces before hitting the ground. The impact of the largest chunk, with a weight of about 450 tons, resulted in an almost perfectly ring-shaped crater. Its diameter is about 110 meters, and the maximum depth may reach 22 meters, as measured from the crater rim down to the crater floor. The depression is today filled with water forming a lovely small lake. Large, upwards tilted dolostone blocks protrude at an angle of 30 to 40 degrees from the crater's depression slopes, giving an impression of the magnitude of impact blast. Actually, the impact that targeted at Silurian dolostones was so powerful that both the iron meteoroid as well as target carbonate rocks were vaporized instantly. This is the reason why no pieces of iron meteorite have ever been found in the main crater area. However, the mining engineer, Ivan Reinwald, was fortunate to find small meteorite particles while he was exploring the shallow satellite craters, and thus the meteoritic origin of Kali craters was proved with full certainty in 1937. Altogether, about 2.5 kilograms of tiny meteorite fragments have been collected so far, and the largest piece ever found weighed only 28.4 grams after cleanup. Chemical studies have revealed that in addition to iron, it also contains substantial amount of nickel, 7.2%, and several rare elements, including gallium, germanium, iridium, rhenium, platinum, and gold. Next to the Kali main crater is located the Kali Visitor Center, where people can get acquainted with meteorites and the local geology. The neighboring island of Hiiumaa hosts a considerably larger meteorite impact crater, but unlike the Kali craters, this crater is buried under sedimentary rocks of the Ordovician age. Nevertheless, the 4 kilometers wide Kärdla crater is thoroughly studied by geologists through a great number of drill cores, and the surrounding, slightly ellipsoidal, more than 15 kilometers wide ring fault can also be seen on aerial photographs. The Kärdla impact occurred 455 million years ago when a meteoroid, about a half a kilometer in size, hit the shallow epicontinental sea and pierced the Precambrian basement rocks to a depth of 280 meters, after first piercing the 140 meters thick sequence of Cambrian and Ordovician sedimentary rocks. The impact event formed a crater rim that is up to 250 meters high, surrounding the 400 to 500 meters deep central cavity. This depression was almost instantly filled with brecciated rocks deriving from the collapsing crater rim and with sediments transported to the depression by back-surged seawater. Normal marine sedimentation resumed soon after the impact, filling the structure and completely covering the crater rim in about 7 million years. The Neogrund structure was recognized as an impact crater only 15 years ago. It is located offshore in northwest Estonia, less than 10 kilometers northeastwards from the island of Osmussaar, Odensholm. The crater shows a well-developed, rather wide multi-ring rim composed of uplifted crystalline rocks. The roughly 4.5 kilometers wide central depression is filled up with lower Paleozoic sedimentary rocks forming a cork-like cap. It should be mentioned that no boreholes have been drilled through this cap as yet, and thus most rock evidence is derived only from samples collected by divers. The impact origin of both the Kärdla and Neogrund craters has been confirmed by findings of planar deformation features in quartz grains. The 6.8 kilometers wide Lumparn crater is hosted by the roughly rom-shaped Lumparn Bay, located some kilometers northeast of Mariehamn, the capital of the Öland Islands. This unusual geological structure, showing numerous scattered limestone boulders on its shores, was a puzzle for geologists for a long time, until an impact origin was confirmed by findings of impact-generated glassy material from the drill core in the central part of the bay. The exact timing of the crater formation is unknown, however. Most probably it was caused by about a half-kilometer wide asteroid in the middle Paleozoic. The 6.6 kilometers wide Söderfjärden crater forms an almost perfect ring-shaped depression at the southern limits of Vasa town on the eastern coast of the Bothnian Sea. The 5.3 kilometers wide crater floor is nowadays used as farmland, and thus offers a particularly impressive view from the air, showing a great number of radially distributed agricultural fields in the crater center. Drilling in the mid-1970s revealed that up to 74 meters thick quaternary sediments overlying more than 200 meters thick sequence of siliciclastic sediments of Cambrian age which rested on brecciated Precambrian crystalline rocks. The examination of drill cores showed the presence of a central uplift area about 1.4 kilometers wide that rises about 300 meters above the crater floor. Identification of shocked quartz crystals in allogenic breccias from the drill core samples in the central peak area justified an impact origin of the Söderfjärden crater, which formed about 530 million years ago. By now, more than 5 meteorite structures have been identified by geologists in Sweden. Among these, the Lochne crater near Östersund town in Jämtland and the huge, more than 50 kilometers wide Siljan crater in Dalarna are the most thoroughly studied examples. Along the Swedish Baltic Sea coast, only one impact structure has been recognized, located on the bottom of Tvären Bay, about 70 kilometers southeast of Stockholm. The 3.5 kilometers wide, almost circular Tvären Bay hosts an underwater impact crater with a diameter of 2 kilometers. The Tvären 2 drill core recovered in 1991 yielded a 140 meters thick sequence of impactites and secular sediments. The target sequence at Tvären consisted of Ordovician carbonates resting on poorly lithified sandstones of early to earliest Middle Cambrian age, covering a crystalline basement. Based on detailed paleontological studies, the impact occurred in the late Cukrous age, corresponding to the lowermost upper Ordovician. As you were able to see in this short overview of meteorite impact craters from the Baltic Sea islands and its coastal areas, this area has been hit by numerous asteroids in Earth's history. So when traveling around, why not take a closer peek at these cosmic guests?